So let's get started. Yeah, so let's talk about decreasing the size of the root file system. So my name is Sergio. I'm located in São Paulo, Brazil. I've been working with embedded for almost 30 years now. I have a company called Embedded Works, where I do consultancy and training on several different embedded Linux topics. Before we start, so the idea of this talk is to talk a little bit about how to decrease the size of the root file system. We will not cover things like decreasing the size of the kernel, bootloaders, and all of that other embedded Linux components. I also will not talk about different types of file systems that you can use to generate a very small root file system image, and not also hardware optimization. So I will really focus on decreasing the size of the software components inside of the root file system. And it's also important to mention that there are always trade-offs, right? So that doesn't mean you should always do this, right? Because if you remove stuff, you're gonna probably lose some functionality, right? And there are always trade-offs, and you always have to think about this. This talk is also kind of beginner talk in a sense because I want to cover some concepts, right? And some nice tooling that can help. So hopefully, for those that are starting, can learn something. For those that work with Yocto for lots of time, can also learn something during this talk. Um, all right, so I have more than 50 slides, and I don't have time to cover everything. So you can always go to the slides later and read it. I will cover the most important things here. Um, so I guess everyone here knows, right, what a root file system is, right? It's one of the core components of the embedded Linux system. You have there the main directories and files. It is mounted by the kernel or maybe via a run disk, and it's kind of standardized, right? There's a few standards like the FHS that defines the main directories and the organization of the root file system. Of course, you can really have very different file systems, right? You can have a pretty much a small file system with just BusyBox and libc. You can have those big file systems that you can see on Linux distributions. You can even have a root file system with just one binary, right? Just one init application that would be Lincoln LED. So it doesn't matter from the kernel perspective. It doesn't matter what you have it. The kernel just expects to have an init binary to run at boot time. Uh, does it matter before we talk about this? Does it matter to decrease the size of the file system? I mean, it depends on the requirements. You might want to decrease it because you want to use less storage. Maybe because you want to decrease boot time because that is less stuff to run at boot. Maybe it's because of performance, right? Because if you have binaries that are smaller, then you use less RAM, for example. Maybe it's because of security, right? Less stuff. So you decrease the surface attack of the system. Maybe because of license, you want to decrease the amount of components there because you want to remove, let's say, GPLv3 from your system. So you might have different motivations for that. This is a few comments that you can run right now and build a Linux system with Yocto, right? It's not that hard. So you can just grab Pocky and then search the environment script and then just configure the machine that you want to build and then make an image and you're done. You can just run it in your system. So what is the size of the full image, right? And here we are talking again about using Pocky as the distro, QEMU x86 64 bits, and core image and minimal image. And then you have a root file system with 1028 megabytes in size. How far can we go decreasing that image though? So that's the topic of this talk. And here we have to talk about requirements, right? Because of course we could have a zero size root file system. That's possible. But it will probably be not that useful, right? So let's say we want a very small root file system that can boot successfully, that can get us into a shell, and we can run some simple commands like ps, top, cat, grep, So that's our main requirement. So that means maybe just BusyBox and libc, for for example. Let's see if we can get there, right? Because the initial image, we have much more than that, the default image, right? With the configuration that we have here, right? About decreasing the size of the root file system, we have mainly two approaches. You can remove components from the image, and or you can decrease the size of the components, right? So you can remove a binary, or you can decrease the size of that binary. So there are just two approaches that you can focus. About removing components, in the OpenEmbedded Yocto perspective, you have to work on three different dimensions, right? You have the distro configuration, the machine configuration, and the image configuration. And then they are kind of orthogonal, right? And one can impact the other. So you have to work with the three dimensions, and we're going to talk about this here. About software optimization, basically you have to work with a compiler and different compiler optimization um, options, right, to decrease the size of the binary. Or maybe you could also replace binaries, right, with implementation that are smaller. So that's another option as well. Let's talk first about removing the components from the system. So this is one of the important concepts, right, in OpenEmbedded Yocto. So the main artifact when you process a recipe is a package or multiple packages, right? So a recipe takes the source code and then creates software artifacts with that, binaries, shared libraries, tables, documentation, etc. And those goes to packages that goes to a feed. And that feed is used to generate the image. So if you want to remove components from the image, what you want to do is to remove packages from the image. That can be done at the distro level, at the machine level, and at the image level. So let's talk first about the distro level. So a distro in Yocto, OpenEmbedded, it's a kind of policy for generating the embedded Linux system, right? It defines the base configuration, right? The overall features of the image that you want to create. Pocky, we know that's the reference distribution. And of course, if you want to have more control, and also if you are building a production system, you will probably not want to use Pocky. That was actually mentioned a few times during this event. And you're going to probably want to create your own distribution. Those are a few variables that can be used in the distribution level to change or include packages, right? That can cause the inclusion of packages in the image. I will not go over all of those variables. Of course, you can just check the slides later or check the documentation, right? But for example, depending on the niche manager that you select, if you select system D, you're going to have much more packages and much more software installed than if you select, for example, BusyBox as your niche manager. In a distro, you can select packages as well, for example, using distro extra rdepends. So all of those variables can, as a consequence, cause the installation of additional packages in the image. Another important concept, let's say you want to know how to check the value of a variable on your current configuration. That can be done currently in two different ways. So you can use the -e parameter from bitbake, or you can use the bitbake getVar command. And that's very, very useful for those that work with Yocto. We run those commands multiple times per day. And here you can see like the current value of those variables that I mentioned, right? So distro related variables that can impact the installation of packages. So here by default, we have sys5 init as an init manager. We have package root core boot installed by default any image that's based on Pocky. There is also as well a kernel module there and lots of different distro features enabled. So let's create our own distro. Let's call it tiny rootfs, our distro, and let's remove everything. Let's see how it goes. Right, so this is my distro. I'm based on Pocky. Usually I don't do that. I usually create one distro from scratch without using Pocky. without requiring Pocket or something like this. But to make it simple, the slides, so that's what I'm doing. So I'm just including Pocket here and then changing it to my needs, basically removing everything like I don't want any extra packages, I don't want any distro feature. Let's see how it goes. So all of the variables are empty now. And then what is the consequence? Well, just 1 MB inside. A few packages were removed, as we can see. It was 35, now it's 26, right? But just 1 MB in size. All right, let's keep moving. 1 MB is not perfect, but we might ask, what was removed, right? There is another very nice feature provided by the Yocto OpenEmbedded, that is build history. That tool, like everyone should use it, because it really helps you to track changes in images, SDKs. You can really track changes, the impact of a change in your metadata and in the output after processing that metadata. So you can track changes in packages, in file sizes, and everything. So let's say I want to understand what happened here, right? What packages were removed from the image after using my own distribution. Then I can just use build root. Build history for that. There is a script there, build history diff, that I can use. It makes it easier because by default, build history will commit. If you enable it, it will commit the changes to a repository. Then you can just go there and do git diffs. But you can also use build history diff for that. It makes it easier to see the output. So here we can see we decreased the image in just 3%. We can also see the change in the packages, which is nice, right? So we can see that basically the main change here was that we move it from sys5 init to busybox init. We're gonna use this in the rest of the presentation. So we have now our custom small distro. What about the machine? So a machine is another configuration file, another metadata that makes it possible to define information about the hardware, right? From the CPU architecture to the components of the hardware itself, the kernel that you want to use, the bootloader, and everything in the middle, like related to the hardware. You also have variables that you can use in a machine that can impact the image, that can cause the installation of package in the image. So here we have basically 6 variables that can help you, like that can be used to install packages and images. So you might want to check those variables if you want to decrease the size of the rootfs. Here is the current value, like for QEMU, right? That's the machine that I'm using here in the tests. I can see that it is installing this v86d package. There are no recommends, no depends, a few kernel modules there, and a few machine features. What I want to do this is I want to overwrite all of this, right? So let's remove everything. I don't want it. I just want a small system that boots into a terminal. So let's see how it goes. For that, instead of creating a new machine, I'm just overriding those values from that machine, right? So I included a file in my distro, and then I'm overriding those. But possibly in a real system, I would create my own machine with those changes. Now we can see all of the values like they are empty, so there are no kind of packages being installed by the machine in theory, right? Let's see the consequence of this. So now I build my image again, and then we decrease it in half. So half of the size, 15 megabytes now. And we also decrease the number of packages, as we can see, right? All right, half of the image. Now, if we look at the output of build history, then we can see we decreased the image in 45%. And if we do a complete diff, we can see that mostly we removed kernel stuff. The kernel image, that was in the image, and also kernel modules. And the image boot, because to boot the image from QEMU, you don't need that, right? But of course, if you are doing a real system, you're going to have to think about this, right? Like, do I need those kernel modules? Do I want them in the root file system? Do I want them enabled built-in the kernel? So we're going to have to think about this. For our requirements, we don't care. Let's disable it because we just want to decrease the size of the root file system. Now, the last part is the image recipe, right? So this is where you have the most control of the contents of the root file system. An image recipe is just like another image, but it's an image that generates for you the root file system. So there you have several different variables that you can use to control the content of the root file system. We are using here core image minimal. That's one of the images provided by OpenEmbedded core, but of course there are lots of different image recipes there, and usually, most certainly, you're going to create your own image recipes in your projects. Possibly most, you're going to create several different image recipes for different purposes, right? So that's pretty much common. There you can use image install and core image as install to define the package that you want to install in the image. You have also image features, right? To enable features in the image. Depending on the image feature that you enable, you're going to have extra packages installed in the image, and so on. So here we can see the default value, right? So in the image install, we only have a package group, core boot, and if we inspect the dependencies of this package group, we can see the packages that are going to be installed by this package group. So those are the packages that are going to the image, right? We can also see the other variables. Only debug tweaks are enabled. I didn't mention, but I'm using here scarf gap in my tasks, right? That we still have debug tweaks, but it was removed. All right, let's decrease. If you look at the packages here, there are some stuff that we don't want, like UDEV. I don't want UDEV. Maybe update alternatives, right? I just want a small system with BizBox and VDC. One thing that we might ask is, what do we have inside those packages, right? Because you might need this information to decide, should I remove? Should I remove NetBase? Should I remove this? Can I remove this? There is another nice tool that you can use, call it UI PKJ Data Util. That is a very nice tool that makes it possible to map the relationship between recipes and packages and files. So you can answer questions like, what are the packages provided by this recipe? Who is the package responsible for this file in my root file system? So it's a very nice tool that can map you this relationship, again, between recipes and packages and files in the file system. So for example, I can answer that question. What do I have inside NetBase? So I can see I have a few configuration files there. I can also inspect the package itself and see, for example, the size of the package, right? And here is the update alternatives package, and here is the UDEV package. We can see here that the UDEV package is very big, almost 2 megabytes in size. So we don't want it. We might want to remove it. So what we can do here, let's create our own image, right? Let's create our own image. Here we go, removed a few things. Now we have less packages installed, right? Let's build it. All right, 6 megabytes in size, the root file system. It's all important to test. The image is still boot, so that's good. With only 6 meg in size, and we have there the command because we have BusyBox, so it's still not only boot, but it works. If we look at the output of build history, we can also see the difference, right, in size. Like we basically cut the image size by half. We can also see the packages that were removed. Very nice. Can we go farther than that? I mean, we created a custom distro, a custom machine, a custom image recipe. Yes, we can. We can, for example, inspect the manifest file, the package is installed, and see what we have there. Can remove something from here? Um, I don't know. I mean, we will need to understand, for example, what is this tty run package? I didn't install it. Why it is there? Because of dependencies, right? So it goes to the image, not only the packages that you select, but also the dependencies from those packages, right? So you have, for example, recipes that depends on other stuff, and then the dependencies are installed as well. If you want to track dependencies to find out why a package is being installed, so you can first generate a dependency graph with bitbake-e, and then you can use another nice tool from OpenEmbedded called OE depends dot that is able to show you the dependencies and answer you the question why this package was installed. So here I'm doing this, right? I took my small like core image tiny image recipe, I built the dependency graph, and here I can see why tty run was installed because of BusyBox needs tab, right? So my core image tiny is including BusyBox in the image, which includes BusyBox niche type, which depends on tty run. So it's a nice tool to track those dependencies. Now, running that tool, for example, against this package, I could not find the dependency. So as far as I could understood, and OpenEmbedded wizards there might confirm that or not, but this is because it's an R recommends, not an R depends. And the R recommends doesn't go there to the dependency graph. Um, so there are two packages there that were installed via R recommends. And that's another variable that can be used in OpenEmbedded. You can just recommend packages. If there is someone providing that package, it will be installed. So if you want to decrease the size of the image and remove the recommendations, you, for example, can use no recommendations. So I have done that with no recommendations, and then I got a smaller image. A little bit small, right? And I can see now I have 80 packages installed. All right. I could go, I mean, on and on removing packages, but I think it's enough about removing packages because the point was to show you the process and the tooling. Now let's talk about software optimization. We have just a few minutes. So you can also optimize the size of the root file system by optimizing the software that you have there. By that, I mean, you can replace software with lighter implementations, or you can also rebuild software with a focus on size optimization, right? And if you look at Pocket-Tiny, it's another reference distribution provided by Yocto. You can see like some examples on doing that, right? And that's basically what I'm doing here. So instead of using glibc, that's basically the biggest package in the image, right? Almost 5 megabytes. Let's use Muscle, that's much lighter. And also, let's build the software with optimization, optimized by size, right? The default um, build is -02. That's a balance between size and speed. Let's do it by size because we want to focus on size. So doing those two changes in my distribution, what happens? I get a root file system with 2 megas inside. So we got from 28 mega to 2 mega. And it still boots, and it works. If we look at the beauty history output, we can see the differences and basically what has changed. We moved from libc, almost 4 megabytes in size, to Muscle, 500K in size, much smaller. And also BusyBox got a little bit smaller because we enabled size optimization in the build. All right, so that's the summary of our optimization, right? From 35 packages to 8 packages, from 28 megabytes in size to 2 megabytes in size. And we could go further, of course, if we want, but at some point we're gonna have to stop, right? Because we don't have enough functionality in our system to make it work. Closing thoughts. Um, the main objective here was to show you that life's a journey, not a destination. So although our destination was to improve the size of the root file system, I want to explain some concepts, right, about packages and the tooling around it. Some general tips. Always start with the low hanging fruits when you talk about optimization. Avoid overcomplicated hacks. That's very important because you will not be able to maintain that later. And of course, Yocto will not bloat your system. I mean, you have really all of the flexibility you need to do what you want with the image. It just require you a little bit of knowledge and patience. If you want to try it yourself, that layer that I created with those metadata, it's my GitHub. The link is there in the slide, so you can just get there. And if you want, provide me some feedback. Hope you enjoyed the talk. And not sure if you have time for questions, but I'll be in the chat answering questions.